properties not found in nature, which is achieved through plasmonic scattering. Metamaterials further move photonics in the direction of full-scale integration, meaning optical chips can become more and more commonly used in consumer-grade electronics such as phones and laptops. And here's a 3D render that depicts a metal material bending light in different ways, depending on which direction it's moving through the material. Over here, it's diffracting in one pattern, it's rotating this way, and over here, the information is changing differently through the material. So before spintronics, MOS transistors in modern computers suffered from several problems that significantly shortened their lifespan, such as charge trapping and electromigration. In addition to this, power consumption was an issue, even when the machine is turned off, because of static power consumption. Spintronics is in the process of fixing many problems associated with how computers store data today, and photonics is a promising candidate to break through the limits we are currently reaching as we further scale our current computing hardware. So conclusions, in the conclusion section, we have, for biocomputing, DNA computing is a much debated contender for the replacement of traditional computing. Neuromorphic computing in particular, however, is less mature and requires more research and development before it becomes advantageous to use over traditional computing. And neuromorphic computing is basically just like using the human brain and brain-like computation. Nanocomputing is inevitable as industries continue to scale down chips, fitting more and more transistors and circuits that have to be in the nanoscale to reasonably fit the capacities that are being aimed for in the industry. So like billions of transistors on a single chip. And nanocomputing is actually related to all three of the other topics, so it's pretty important. For spintronics, spin transfer torque is one of the most promising breakthroughs, as we discussed earlier, and it's used for spin-based circuits and switching mechanisms. MRAM is also being implemented, and it's on the market right now, and it's the results have already been proven as of 2020 and beyond. Photonics technologies provide a possible solution to the end of Moore's law, and they allow for further scaling down of integrated circuits as well as faster computation and data throughput.
The title of the article I reviewed is Towards Parallel Quantum Computing, Standard Teleportation Algorithm is, in some reasonable sense, unique. And it was done by some researchers at the University of Texas at El Paso. First, it explores the possibility of parallelizing quantum computing. The only way to speed up computation on modern computers is to decrease the size of memory and processing cells that form a computational device. However, new quantum computing algorithms have been developed that use quantum effects to speed up computations without these trade-offs. We can make further improvements by parallelizing quantum computing. This could be done by transmitting the quantum state from one processor to another. In quantum computing, this is known as the teleportation algorithm, and its efficiency is unknown. This paper shows that the teleportation algorithm is possibly the only algorithm for parallel quantum computing. They also explore the need for parallel quantum computing. So there are many practical problems that require data processing at a rate way above our modern data processing speeds. For example, computational models can predict where a tornado will move in the next hour. However, the processing takes longer than an hour, so it would be practically useless if it didn't have quantum computing speed. We also must compute many predictions based on different situations. This uncertainty requires further computation. Computers can only read from memories at a limited velocity. The current solution is to increase speed, is to make computational components smaller, which is inefficient. There are also problems when parallelizing quantum computing, such as measuring an object at the atomic level. It will only provide a result that is probabilistically predictable. However, despite this problem, computer scientists were able to rearrange corresponding computations to increase speed. So while quantum computing is fast, the integration of parallelism can make it even faster, leading to diverse problem-solving capabilities. Teleportation is needed for computers in different geographical areas so they can exchange quantum states. However, the efficiency of teleportation is unclear. To understand parallelizing quantum computing, it's important to first understand some key components of quantum computing. Parallel quantum computing utilizes some key components such as superpositions of ordinary states that correspond to a qubit, composite states that work together using qubits. For example, in binary, 0, 1 would pair to be denoted as 0, 1. However, in quantum computing, these values would be superpositions of 0 or 1, which could be represented as 0 exclusive or 1, making the pair equal to a superposition of these values. So it would be 0, XOR 1, XOR 0, XOR 1 would be the pair, and they could be restructured and represented as linear combinations. So in quantum computing, physically possible transformations must satisfy two conditions. Superpositions get transformed into similar superpositions, and also another mathematical property needs to stay constant. Measurement process is a method of detecting the quantum state by using the system's probability amplitude. So standard teleportation algorithms allow communication between the sender and receiver. This is straightforward in classic physics, but a challenge in quantum physics. Teleportation in quantum computing is made possible by preparing a dependent entangled state between the sender and receiver. A more general entangled state will not work for teleportation. The only way to communicate between point A and B includes constructing an entangled state between A and B. The only successful entanglement for communication is part of the teleportation algorithm due to its unique characteristics. This makes the teleportation algorithm the only known viable algorithm for quantum parallel computing, although its efficiency is currently unknown. In conclusion, the implementation of parallel quantum computing may only be possible using the teleportation algorithm.
So for part 2 of the project, we have a research article on photonic integrated circuits titled Heterogeneous Silicon Photonic Integrated Circuits. So as a little background, silicon is a promising material for use in creating integrated photonic chips because it can be used to create nano-optical fibers used to guide light throughout the chip. It also allows for easy integration with current silicon-based electronics. Silicon photonics is seeing major use because it allows for the rapid scaling down of photonic chips and therefore reduction in the latency of data transfer and energy consumption. What is a photonic integrated circuit? Well, a photonic integrated circuit, or PIC, is the optical or light-based successor to traditional integrated circuits, which are primarily electronic. The processes used to create a PIC are mostly the same as with normal ICs, save for the use of different materials that are more suited towards guiding light. Silicon wafers are still used as a substrate to chemically etch out the 3D shape and design of the integrated circuits, but there are a few differences with photonic integrated circuits, which we will go over shortly. So here are the manufacturing details, a few details about how a PIC is made. So heterogeneous integration allows for reduced manufacturing costs due to economy of scale and allows for better performing devices due to the reduced travel time of the photons throughout the chip, and therefore the reduced travel time of the information in the chip. And light is generated on the chips by doping dielectric thin films with rare earth ions. An advantage of using silicon as a substrate in photonic chips is the ability to amplify higher bitrate signals without causing patterning artifacts. And also, we're very familiar with using silicon in electronics already, so it's nothing too risky compared to other more novel methods. Over here, you can see an outline of the general process towards making a silicon wafer and like a photonics integrated chip. You can see the waveguides and everything that goes into this to the substrate. So for scaling and parallel computing, we have, as photonics chips are further scaled down and more cores and transistors are fit onto each die, which is a thin slice of the wafer that is ultimately used in the end microchip, they become more power efficient. And however, more cores also means more interconnects have to be made between the cores. But currently, interconnects between cores are achieved electrically, which limits the data throughput between cores, even though the computer logic is happening very fast in between the cores, or in the cores themselves. It can't be transferred between the cores very efficiently due to that being done electronically. And when the wiring fills all the available space, the capacity cannot be increased by changing the size anymore. Integrating photonic chips with other electrical components of the computer continues to prove itself challenging in photonics. Over here, you can see a small outline of how, or comparison of how a photonic integrated circuit compares to a traditional or CMOS integrated circuit. Passive optical components. There are many different types of passive optical components that can be built on silicon. Various examples are optical waveguides, couplers, multiplexers, polarization control devices, filters, resonators, etc. These components all come together to form the photonic integrated circuit. For waveguides in particular, silicon and silicon oxide are suitable materials for very large-scale integration with VLSI due to their high index contrast and high confinement properties. And over here, you can see the use of those materials and the waveguide itself. And this is displayed at a scale of 10 nanometers, which is very magnified. So you can actually see what's going on with the waveguide. Final conclusion. The use of heterogeneous silicon in the integrated chip creation process allows for a wider variety of things to be achieved, such as more sensors on chips, such as gyroscopes, magnetometers, and more. Higher potential for large-scale integration of photonics integrated chips, better performance and energy efficiency, and lower manufacturing costs due to our familiarity with silicon, as I mentioned